Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 12, Lesson 1, Measuring Chance with Ratios. Unit 12 is our last unit in Math 6 and it's on probability. And probability is all about measuring the chance that something happens. And what we're going to see today is that oftentimes that measurement occurs with a ratio, with a fraction. So let's jump right into it. Now, we can measure the chance that something happens by what is known as using a probability ratio, okay? And again, we're always going to be expressing these ratios, at least in this lesson, in terms of fractions. So let's jump right into it and see how we do that with a classic case of marbles in a bag. Let's take a look. Exercise number 1. A bag of 12 marbles contains 3 red marbles, 4 blue marbles, and 5 white marbles, all the same size. Nora reaches her hand in and pulls out a marble at random. Letter A. Which marble is Nora most likely to pull out and why? All right, well, I'd like you to answer question A. This should be something that should be pretty easy to think about, but why don't you pause the video and see what the answer to A is. All right, well, I'm hoping that you said a white marble, right? And it's very simple. There's more white marbles than any other type of marble. That's it. It's that simple, right? So white marble, because there are more of them than any other color. All right, simple enough. Let's take a look at letter B. Express as unreduced fractions the ratio of the number of each color marble to the total number of marbles. All right, this is simple enough, right? Right, we just want to know the ratio of the number of reds to the total number of marbles in our first case. So we've got 3 red marbles, we've got a total of 12 marbles. So the ratio of red to total marbles is just 3/12. Real simple, right? Why don't you go ahead and do this for blue and white? All right, so what do we have? Well, we have 4 blue marbles, so that's 4/12, and we have 5 white marbles, so 5/12. Now, if you're thinking to yourself that each one of these is actually the fraction of how many marbles are red, blue, and white, then that is actually fantastic. In other words, 3/12 of the marbles, which is 1/4, but whatever, 3/12 of the marbles are red, 4/12 of the marbles are blue, and 5/12 of the marbles are white, right? Simple enough. How many red marbles are there? Divided by the total number. How many blue marbles are there? Divided by the total. Now, one thing that's key here is that all of these marbles, right, are the same shape, and the idea is, right, that Nora is closing her eyes, she's reaching her hand into the bag, grabbing a marble, and pulling it out at random. All right, in which case we've got these fractions. Now, let's see where we can go with these. Now, the chance, or what we call the probability that something happens, can be measured using these ratios as long as we have what are known as equally likely outcomes. You're going to hear that term a lot both in Math 6 probability and every other time you deal with probability in future math classes. Equally likely outcomes. So like in that last problem, right? Every one of the marbles being the same size was as equally likely to be pulled out of the bag as any other marble. Now see, if some of the marbles were like larger or smaller or whatnot, then they may not be equally likely because I might decide, there's that big marble, I'm gonna grab that one, or that small one, I'm gonna grab that one. But given that they were all the same size, there's really no way, if we're closing our eyes and pulling one out at random, that we can possibly, know which one's which. So let's now do some probability ratios. Exercise number 2. Keeping with the marbles in the bag above, if Nora pulls out a single marble at random, state the probability that blank. All right, so here's where we're actually going to be writing down some probabilities. Now the great thing is, All the probabilities that we're going to write down here are very similar to what we just did. All right. In fact, the probability that the marble is blue, the way that we literally measure that is by saying, well, I've got how many blue marbles? Let's actually get this down. We had 3 red, 4 blue, 5 white. So 3 red, 4 blue, and 5 white. So the probability that the marble is blue is simply 4/12. Now, you could also write that down as 1/3. That's fine. A probability ratio is a fraction. Oftentimes it can be left in its unreduced form. Sometimes your teachers will want you to reduce it. If it doesn't say you have to reduce it, either one of these answers is great. The probability a marble is white, that's 5/12. Ratios are so common in probability that you will even start to hear teachers look at this fraction, and instead of calling it 5/12 or 5/12 or anything like that, you'll actually hear them say things like 5 out of 12, right? So 5 occurrences out of 12 occurrences, the marble will be white. 4 out of 12, the marble will be blue, and 3 out of 12, the marble will be red. Right? That also will reduce down. That would be reducing down to 1/4, but again, the unreduced fractions are fine as well. Now, let's continue with this bag of marbles, but let's look at some probabilities where it isn't just what's the probability that it's white, blue, red, etc. Letter D. What is the probability that the marble is not red? All right, well again, the probability that is not red, we want to count up all the equally likely outcomes where it's not red. Well, there are 3 where it's red, and that means that there are 9 where it is not red. So the probability that the marble is not red will be 9/12. And again, that would reduce, if you want, to 3/4, but 9/12 is good as well. Well, let's take a look at the probability the marble is not black. Well, we're going to look at all of these marbles. We're going to count up how many of them fall into the category of not black, and that would be, well, actually all of them, right? So the probability that it's not black would be 12/12, which you could also just express as the number 1, right? It's actually a guarantee that the marble won't be black. And one very similar to letter E, what is the probability that the marble is green? Well, if I look at all of these and I count out how many of them are green, that would be, well, it'd be 0, right? So the probability that the marble is green will be 0/12, which you can write down as 0. Now, by the way, those last 2 are very important, right? We are guaranteed there's a 100% chance that the marble won't be black. So the probability it won't be black is 1. We also have a 0% chance, or there's just no chance at all, that the marble will be green. So the probability the marble is green is 0. All right? And those are the 2 extremes of our probability scale, 0 to 1. And this actually gets into the next question, or the next exercise. Exercise number 3, let's take a look. Looking at your fractions from exercise number 2, how can you quickly tell that none of them are larger than the number 1? Right? This is very, very important. Okay, probabilities cannot be larger than the number 1. Now, granted, you might eventually express a probability in terms of percent. Like you might say, well, the probability it's going to snow tomorrow is 25%. But that's actually the number 1/4, right? That's really the ratio 1/4. So that's certainly not greater than 1. But in a bigger picture, how can you look at every one of these fractions and know that none of them are bigger than 1? Think about that for a moment just in terms of fractions. All right, well, the only way that a fraction can be larger than 1 is if its numerator, the number on the top, is bigger than the denominator, the number on the bottom. And in none of these cases is the numerator larger than the denominator. And that kind of makes sense, right? The denominator is literally how many equally likely outcomes do I have, right? And then the numerator is how many of my equally likely outcomes, right? How many of the ones in the denominator fall into the category that I'm trying to find the probability of. So there's no way for the numerator to get larger than the denominator. I couldn't have 14/12 here. It would be impossible for 14 of the marbles to fit into the category when there's only 12 total marbles, right? The best I could do would be have something like 12/12, which would be just equal to the number 1. So at the end of the day, right, how can you quickly tell none of them are larger than the number 1? Because none of the numerators, well, I'm going to just write down tops, are larger than the denominators. And let me get rid of a little bit of the red there. Numerators. There we go. All right. Very, very important. When we measure probabilities, right? When we measure probabilities, they always go from 0 to 1. So let's talk about probability and chance. Probability is simply a measurement of the likelihood of something happening, right? How likely will something happen? And it's important in the real world that we have the ability to measure chance. And you see it all the time. Oh, there's going to be a 25% chance that it's going to rain tomorrow. Or, you know, this basketball player typically makes 3 out of 4 free throws, right? You know, we see probabilities all the time expressed as percents and fractions, and later on in this unit, we will express some probabilities in terms of percent work. Today, it's going to be all about fractions as well as in the next lesson, right? So it can have a value, probabilities that is, from 0 to 1, very oftentimes expressed as a fraction, with a value near 0 indicating a highly unlikely event. So, you know, if I said, hey, the probability that I'm going to win the lottery is like 1 in 300 million, well, then that's a pretty low chance, right? That fraction, 1 over 300 million, would be very small and pretty near 0. It's highly unlikely I'm going to win the lottery. And a value near 1 indicating a highly likely event. So like if there's a 9 out of 10 chance, a 9/10 chance that I'm going to cook a meal tonight instead of ordering out, well then it's highly likely that I'm going to do that, right? It's still possible that I might order food out, but highly likely if it's 9/10 of a chance that I'm gonna make my own food tonight, that I'm gonna just make my own food. So let's take a look at this continued emphasis on using these ratios to measure chance. Take a look at exercise number 4. In a dozen eggs, 3 of them are cracked. Zach randomly selects 1 egg. Answer the following questions. Letter A, what is the probability that Zach will choose a cracked egg? All right, well, why don't you go ahead and do that problem? All right, well, what's our denominator? Well, again, it's 12 because Zach's looking at a dozen eggs, right? How many of those dozen, how many of those equally likely outcomes fall into the category we're looking at, which is cracked egg? Well, 3 of them. He really got a bum dozen there, right? So the probability that he's got a cracked egg is 3/12, or 1/4, whichever one you want. Now, letter B, simple enough. What is the probability that Zach will choose an egg without a crack? All right, pause the video now and come up with that probability ratio. All right, well, how many equally likely outcomes fall into the category egg without a crack? Well, if 3 of them are cracked, that means 9 of them aren't. So that probability would be 9/12, or if you want, 3/4. Either one. All right, now finally, letter C. How would you rate the likelihood of Zach selecting a cracked egg? Highly unlikely, somewhat unlikely, neither likely nor unlikely, somewhat likely, or highly likely? Explain. All right, so which one of these, and again, there's really no necessarily right answer on here. Eventually there might be, but right now, just a feel for it. If the probability right? That Zach is going to choose a cracked egg as 3/12 or 1/4, right? Whichever way you want to think about it. Which one of these phrases would you choose to describe how likely it is that he would pick a cracked egg? Well, look at it this way, right? Take a very simple thing. I flip a coin, right? I could get a head or a tail. There's only two things, right? So it must be a probability of 1/2 that I get a tail and a probability of 1/2 that I get a head, right? That would be that sort of like neither likely nor unlikely, right? Now, the probability that he's going to get a cracked egg, well, that's less than 1/2, right? So it's got to be more unlikely than it is likely that he got a cracked egg. Is it highly unlikely? Well, 1 out of every 4 of these eggs has a crack in it, so I wouldn't say it's highly unlikely. You know, I mean, maybe if I had 3 dozen eggs and like one of them was cracked, that would be highly unlikely. But I would call this somewhat unlikely. Somewhat unlikely because the probability is less than 1/2, but still not close to 0. Right. If I said to you, tomorrow, right, the probability it's going to rain is 25%. 25% and 1/4 are the same measurement, right? So if I said the probability it was going to snow tomorrow was 25%, you know, you probably wouldn't say it's highly unlikely it's going to snow. On the other hand, if I said tomorrow the probability it's going to snow is 5%, then you might say, well, that's highly unlikely. You know, there's a 95% chance that it will snow, right? Or that it won't snow, sorry. Whichever one I said. Let's keep going. We'll work more with highly unlikely, likely, all of that in a future lesson. But let's take a look at exercise number 5, which illustrates a very important point. A board game has a spinner with 8 equally sized regions numbered 1 through 8 as shown. Gabriella spins the pointer once and it lands on a number, not necessarily 7. Letter A, what is the probability that the pointer will land on a multiple of 4? All right, well, why don't you see if you can figure this out? It's a good review not only of the probability we've just been working on, but also what multiples are. Pause the video and see if you can do this. All right, well, there are 8 equally likely outcomes, and those equally likely outcomes are landing on a 1, a 2, a 3, a 4, a 5, a 6, a 7, and an 8. So an 8 is going to be in the denominator. Whatever my answer is, one thing I know for certain is that there's an 8 in the denominator. Now, I have to figure out how many of those 8s fall into, how many of the 8 fall into the category of landing on a multiple of 4. Well, multiples of 4 are 4 times 1, 4 times 2, 4 times 3, 4 times 4, etc. So 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, but it's not on there, right? So my multiples of 4 are 4 and 8, and therefore the probability that it'll land on a multiple of 4 is 2/8, or 1/4. All right. Now, very, very important, let's take a look at letter B. If Gabriella was playing a different game with the spinner shown below, why would the probability of rolling a multiple of 4 not be as easy to find as in A? All right, so why would it be that if Gabriella is now using this instead of this, and I'm not even asking what is the probability that it'll land on a multiple of 4, there's going to be no way we can actually figure that out in this problem, but why would it be more difficult to figure it out for this spinner than this one? Pause the video now and see if you can answer this question. Well, it's pretty much this simple. The sections here aren't all the same size, right? Which means these 8 things aren't equally likely outcomes. That's very important, all right? Because numbered sections are not the same size. We do not have 8 equally likely outcomes. So the only way we can really do this counting thing, where we say, hey, there's 8 equally likely outcomes, and 2 of them fall into the category that we care about, and therefore the probability is 1/4. The only way we can do that is if getting a 1, 2, 3, 4, 5, 6, 7, 8, if they all have the same chance of happening. All right, if they all have the same chance of happening, then it's as simple as saying, well, there's 2 multiples of 4 out of a total of 8, so the probability is 2/8 or 1/4 if you reduce it. But down here, these are not equally sized sections, and because of that, they are not equally likely outcomes. So the last question, would it end up being larger or smaller than the value in A? Explain. And let's just be clear about what it refers to. It is referring to the probability of landing on a multiple of 4. So would the probability of landing on a multiple of 4 be bigger for this spinner or for this one? Pause the video now and see what you think. Well, I'm hoping you said larger. And I'm hoping you said larger because the 4 and the 8 are larger sections here than any of the other numbers. They're more likely. You're actually more likely to land on a 4 than a 2 because literally the 4 is twice the size of the 2. And 8 is 3 times the size of these things, right? Actually, landing on an 8 is the most likely thing you could have happen here. But regardless, it would be larger because the 4 and 8 are bigger sections than the others. And that's a very important thing, right? We can only do probability ratios when all of the outcomes that we're looking at are equally likely. If they're not, then it becomes much more difficult to set up these kind of ratios. Let's wrap this up. Probability is one of the most important fields in math because it allows us to measure how likely something is going to happen when we can't say that something is going to happen for certain. When there's doubt, right? And that happens all the time in the real world, right? When we see a batting average for somebody who's playing baseball, that's a probability. When you see something like, oh, their batting average is .357, well, that means 35.7% of the time, they're going to be hitting that baseball, right? At the same time, when we see something like the weather forecast saying tomorrow there's an 80% chance of the weather being sunny, well, again, that is a probability. And then we use probabilities to make decisions, right? We use probabilities to make decisions all the time on how much we want to risk, right? Do we want to risk, doing something based on uncertainty? Well, if we've got a probability, that can help us make that decision. All right. We're obviously going to be working with probability more in this unit. It's a short unit, but we want to just give you this introduction to probability in Math 6 before you do more of it in Math 7 and Math 8. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.